So, is ASAP the only way of doing scheduling? Obviously not, right? So, let us look at another way of doing the same schedule within the same 5 time steps. But now what I am going to do is, I am going to take the opposite tack over here. I know that I will finish within 5 time steps. Let me try and push everything as late as possible. Should be familiar to all of us, this is how we normally work, right? Just do things in time. I am sure all of you are planning to start studying for the exam tomorrow, so that is how we go. I haven't set the question paper yet, so we have the same problem there. But, so as late as possible, what would happen? Operation number 2 alone is fixed, that is guaranteed. Operation 1, the latest time that it can execute without basically pushing operation 2 out of the 5 time units is that it has to operate over here. That in turn means operation 3 is over here, and because 5 and 7 require 2 time units to execute, they are automatically forced into these places. So, in other words, you see that this track which we had already sort of identified as the critical path does not change at all, okay. The operations that were on the critical path can't be moved around. But operation 4 on the other hand, what is the latest time at which it could have been executed, and you still get operation 2 happening in time? It can be done in step 3, time step 3. Okay. Contrast this with what we have over here, where operation 4 happens in time step 2. What does that imply for operation 6 and 8? If 4 happens in step 3, 6 should have finished by step 2, which means it could have started in step 1. So, this is what we call the ALAP, as late as possible schedule, or the ALAP schedule. ASAP, ALAP are how we normally refer to these things. If we go back and do the same computation, number of multipliers, number of adds, what I find is, now in time step 0, I only require 2 hardware multipliers to start 2 multiplications, okay. In time step 1, I again need 2 hardware multipliers. In 2, 3 and 4, I do not need any multipliers. As far as adders are concerned, in step 0 and step 1, I do not have any additions. In step 2, I have 1, then I have 2, and then I have 1. If I look at the max, it is now 2 and 2. So, what this means is, once again, n is equal to 5, number of multipliers that I need is equal to 2, number of adders is equal to 2, hardware utilization efficiency of the multiplier, if you do the computation, now comes out to be 40%, and for the adders is also 40%, right. I mean, I am taking the overall hardware utilization efficiency of all the adders in all the hardware adder units. I can also compute it for each individual adder if necessary, once I have decided which operation is going on to which addition hardware, right. So, there is an improvement, but if you think about it, there is nothing really that we have done over here that actually guarantees any improvement, right. What we have done is we have tried pushing some operations to a later time, but just as we saw that things could have piled up right at the start, right, the 5, 7, 6, 8, all of them could have happened in time step 0. Supposing I had an alternate situation where there were multiple output nodes or multiple nodes that were sort of terminating the graph, right, then what would happen is all of them would end up in the last time step, okay, and my hardware utilization efficiency would drop because I would end up requiring a large number of hardware resources at the last time step, okay. So, it is not obvious that the ALAP schedule will give you a better efficiency or in any way improve the schedule over a ASAP. So, then why do we bother, right? what is useful in this case is it gives us a measure of how some of the operations can be moved around, right. So, if I basically look at this in the ALAP or the ASAP schedule, 6, 8 and 4 would have been here, whereas now they are in one time step later, okay. So, effectively I can define something that I will call the mobility of each of these operations. In terms of the timing analysis that you are probably more familiar with from digital circuits, this is the slack. So, the mobility essentially tells you, look, operation 8 could have been scheduled either in time step 0 or in time step 1 and I can still meet my final constraint. So, up to that level at least I have some freedom. Keep in mind that it is not absolute freedom that I have over there, right, because I can say right now that 6, 8 and 4 all have a mobility of 1. But the moment I make a choice, let us say I decide that 4 has to be in time step 2, that automatically kills the mobility for 6 and 8. Okay. So, it is not as if I have the freedom to make the choices any way that I like. To start with, I have a certain amount of freedom, certain mobility associated with each of the nodes. But the moment I start making choices, that starts reducing the freedom that I have. So, how do we make use of this and how do we go about systematically using this in order to come up with something which presumably should give us better hardware utilization is something that we will look at later. But before that, what I am going to do is take another look at this the original graph and say try and understand what was the problem that we faced over here, right. Can we do a slightly more detailed analysis of this graph? Is it possible to bring the critical path down from 5 to 4, right, or even lower than that? And then based on that, could I have actually modified the acyclic graph in such a way that I could have possibly ended up with the schedule that I wanted.